So our claim is that the classical states each represent a very definite set of variables, and there are no longer any superposition. So between classical physics and variable physics, there is no quantum mechanics left, no superposition. This is very strange, and people when they first heard it, that we don't believe. But this is precisely the whole point. Imagine a planet, a very large planet. The planet is the biggest planet on Earth, and now we take a very, very tiny volume in that. A cubic millimeter of planet Earth. You look at the cubic millimeter of planet Earth, it's still very large in terms of the original ontological states. There are billions of atoms in a cubic millimeter of Earth. Those billions of atoms might eventually form an ontological state. It's just slightly different from the vacuum. So imagine that if you have 1 cubic millimeter, the odds that the chance that it can be distinguished from the vacuum is the chance that it's equal to the vacuum is 1 minus epsilon. The chance is epsilon that you can distinguish it from the vacuum state. Epsilon would be small. But 1 minus epsilon is the chance that you cannot distinguish it from the vacuum. Well, but the Earth consists of billions and billions of cubic millimeters. So I have to raise this with very high power. And then of course e to the minus epsilon n, where n will be much, much bigger than 1 over epsilon. So the odds that you can distinguish the entire Earth from the vacuum state is basically 1. We will certainly be able to distinguish planet Earth from the vacuum. And that is in terms of the ontological degrees of freedom. When looking at things this way made me decide that it should be possible to, when you have to look at the classical state like these, it should be possible to say, well, the variables will be different in all these, and whether the cat is dead or alive, the variables will be distinguishable. Whatever the dial of a detector says, the variables will be distinguishable from each other. And that is this picture, that every single classical state corresponds to a number of variable states, but those do not overlap with the variables of other classical states. And that means that when you measure something, what we really mean is the thing becomes classical. It becomes, there are so many variables that take a different value from otherwise that the uncertainties all disappear. And that's my definition of classical. So the measurement, in principle, measurement should be straightforward. And on top of that, now imagine that you have a, and this is, yeah, how I say, okay, suppose I have an in state. And I think I have to describe these three now in one go, otherwise I lose too much time. So imagine that, imagine doing experiment in two different ways. We look at it totally classically, as if we never heard of quantum mechanics. If you haven't heard of quantum mechanics and you're describing an experiment such as the LHC, there are photons coming in this direction, photons coming in this direction, and some of these animals collide and detect the collision debris. Now, what are you doing with these ingoing protons? You don't know exactly where they are going. So actually, the ingoing protons have a probabilistic distribution, and it depends on the depth of distribution, you know, how the scattering data will emerge. So there will be millions of different results of scattering. The particles scatter different in every collision, and we are collecting the statistics, and that's what LHC is doing. So the fact that LHC is collecting statistics has nothing to do with quantum mechanics. But when we do quantum mechanics, we say, well, wait a minute, no, these ingoing protons are perfect plane waves. Here's a plane wave, here's a plane wave, and we look at this plane wave as a superposition of the variables. We're using templates instead of variables. The templates put the variables in plane waves with particles going in, and then we compute what comes out. And what comes out is basically spherical waves, S waves, D waves, you name it, but basically, and then we say, now we have a detector here, and if the wave is spherical, there's only a very small chance that the detector will go off, because odds are that the particle moves in another direction, and the detector does not go off. So many detectors do not go off, some do go off, but the way, the question which will go off or not, depends on, well, you have to compute your quantum amplitude of the spherical wave getting out, and that gives you the probability that the detector goes off. And that, of course, Born's rule of probabilities, that you can produce quantum amplitudes. But so you see that the outcome of the experiment is basically the same when you have a classical argument or a quantum argument. Only in quantum argument you use your language differently. You say that probabilities come out in the very end when you compute the Born amplitude. Whereas the classical particle physicists would say, no, the probabilities are put in at the very beginning. When I say I don't know where exactly these incoming photons are going. My claim is it's the same thing. The same thing because when we describe this template here, we're using a superposition. But we actually had no good reason to do it at all. It was again our ignorance. These coefficients tell me what the chances are that I have one particular variable going in. But in my new variable basis, which I don't really know, since I don't know that, I never specify these things. But when I describe the inverse in this way, then I have the probability alpha squared, that is variable 1, the probability alpha 2 squared, that it is variable 2, and so on. I put the probability in at the very beginning again, but work with the template, I say, okay, these coefficients are the odds that I start with a particular variable state. Now, in a deterministic theory, these individual beings will only produce ontological states coming out. So some of them will have this detector going off, some of them have this detector going off. It always has chance 1. There's no further statistical distribution. Statistical distribution comes in at this level, but not once you know what the variable is, the other variable will certainly go off or not at all. And so what you do now is you see that in this theory, both the variables and the template psi obey the same Schrödinger equation. So e to the minus I ht on these states gives me the end state, the final state. So the final state is obtained by writing the S matrix, which is derived from the Hamiltonian, and so on. The Hamiltonian is the same here as it is here. So when I compute using the Born amplitude, the Born rule, what the outcome of the experiment is in terms of the templates, I get the same answer as when I wrote psi in terms of the variables. And I say these variables obey the same Schrödinger equation, but this is all linear, so that's why the template also obeys the same Schrödinger equation. So it doesn't matter whether I use these or this thing to compute the in the very end. In the very end, I again take psi with some variable for the out states and take the absolute square. What I'm actually doing is I'm again computing these alphas. So when I have solved the Schrödinger equation, I again got alphas out, which are the probability that the detector goes off, but these alphas are just exactly the squares that I got from the beginning. In other words, if I would use Born's rule at the very beginning of the experiment by writing my template in terms of variables, then I'm allowed to use the same Born rule to interpret the outcome, the final outcome. So the final outcome is I take the amplitude of the state square and I say that's the probability that my detector comes off. That's the measurement. And again, in the measurement, I don't know a priori what the variables are, but now you see that the reason why I get probabilities is that I put probabilities in at the beginning of the experiment when I replace the variables by a template. And for me, this is a beautiful answer of measurement. It actually also is a beautiful explanation as why Born works. Because there's basically no other choice, and of course people knew that for a long time. There's no alternative to Born's rule. If there is, it's extremely ugly and dirty. But here we see that when we work with templates, we can say right at the beginning of the experiment, we define alpha 1 squared and alpha 2 squared and so on to be the probability that I have this variable or that variable. And that defines my template. And well, as soon as you deviate here from the one, you'll be in deep trouble, because we are using unitary transformations all the time to go from one basis to another basis. So since the transition from the Beaver basis to the template basis is a unitary transformation, it's these alpha squares which are invariant under such transformations, which transform the same way. And therefore, it's the alpha squares which come out to give you Boyle's rule. And, well, the collapse of Schrödinger, the Schrödinger cat, of course, is very much the same thing, that when we start an experiment, we describe variables. So in the famous Schrödinger cat experiment with a cat sitting here, and there's a quantum experiment, and well, you know what the Schrödinger cat experiment is. You have a quantum experiment, outcomes a wave function, a detector which measures the wave function, use the Boyle's rule to find out the probability. We calculate that it's about 1 chance and a half that the detector will go off, 1 chance and a half that the vessel of poison will kill the cat, and 1 chance and a half the cat will not be killed. And in the very end of the experiment, there's either a dead cat or a live cat. There's either a dead cat or a live cat. There never is a superposition alpha dead because beta alive. The Schrödinger cat problem is, why do we never see this state? Why do we always see some probability that we have that state and some probability that we have this state? But the outcomes experiment is either this or that, and not just a probability. So, so where do these probabilities come from? And the argument is exactly the same as what I said before. In the very beginning, we worked with templates. And in the templates, we already have hidden our Boyle interpretation of these coefficients. So since they are there in the beginning, and these coefficients remain the same during the entire evolution, because we assume that the deterministic system uses the same Hamiltonian as what we later use for our templates. So the alphas remain the same, and therefore also the outcome of the experiment against probabilities. If we would have analyzed Schrödinger cat problem from the two ontological states, B1 and B2 and so on, I think we chosen only one of them, we would have either found a dead cat or a live cat, but never a superposition. Superpositions never enter. If your initial state is a pure variable state, your final state will also be a pure variable state, and there will be nothing in between. So if you keep that, then all these difficulties will sort out. As for the collapse, it means that indeed I always have, well, if I work with a template, I get a messy wave function where I do a measurement, I measure only one of the variables. If I would start with a state that would be a variable from the beginning, say the beginning of the universe, the Big Bang takes place, and from that moment on, the universe is in a variable state. It will be in a variable state ever after, including the observer who does observations, who does measurements, and so on. They will be in a variable state. And so the wave function that we use to describe the evolution of a variable will always show a variable. So when we do a measurement, we only get certainties, and then we get something vague in between. So assuming that the universe is in a variable, that variable will evolve. Indeed, in agreement with the Schrödinger equation, that was put in by hand, and because it agrees with Schrödinger equation, and because it was a variable, it will be a variable the moment which you measure. And so that variable looks like a collapsed wave function. So the collapse of the wave function also takes place completely automatically. I do not have to put that in. So I think all these issues, which have tremendous amount of literature associated with them, they become very, very easy in this interpretation. It's basically, one could call this a pre-quantum theory. Before people realize all the difficulties of quantum mechanics, this all looks extremely clear. But now, because people refuse to interpret complementarity square linear, they run into these problems. However, I also am very much aware of the difficulties of this interpretation. And the reason why people encounter this problem is that they do not believe what I said here could possibly be true. They do not believe that there's a Beaver basis. I've got many emails people say such a basis does not exist, period. I ask, how do you know? Because you don't. If you understand physics at the Planck scale, yes, but you don't understand physics at the Planck scale. So the notion that they know that no Beaver basis exists, I don't think they do. Because think of these neutrinos are accidentally hit upon one. How do you know that taking not only the standard model, but everything that will be between the standard model and the Planck scale, and take all that gigantic big Schrödinger equation, is there a Beaver basis, an ontological basis for that or not? I think only very technical calculations can give us an answer, and not someone who declares that he has seen had contact with God and God told him there's no Beaver basis. I don't believe that. So, but they come with very good arguments. So I understand his arguments very well, and the main argument is Bell's experiment. Now, Bell's version of the Einstein-Rosen Duncan experiment. And I have not much time to discuss that anymore, but I can just give you the outcome of my analysis. I look at this very carefully because there's a problem here, a big problem. A big problem is that Bell says whatever I've done here is impossible by very rigorous mathematical arguments. The very rigorous mathematical arguments, like all rigorous mathematical arguments in physics, always have some fine print. Because mathematics is an idealization of physical reality. So when they come with a mathematical proof, they idealize something. And what was idealized here was, well, first of all, the notion of free will. And the Bell experiment roughly consists of two things. There's an Alice and there's a Bob. So this is Alice, this is Bob. And here is state S of an atom that emits two entangled particles. And okay, there was a question about entanglement just before. I claim that what I've done here, if you look at these templates, you may entangle these templates as much as you want. Or you can say, I'm just addressing these outcasts, and nothing special happens when you entangle things. In that language. But here, something very strange happens. Two entangled photons are emitted. And Alice uses a polarizer in direction A, and Bob uses a polarizer in direction B. And Alice measures whether the photon goes through or not. A is plus or minus 1. And Bob measures whether his photon goes through the filter or not. And he finds a B plus or minus 1. And you want to compute the average values of A times B for every experiment. As a function of the direction of polarization they choose. And if you do quantum mechanics, you find that this is the cosine of A minus B, or 2A minus B if you have photons. In electrons is cosine A minus B, for photons is cosine 2A minus B. That's because photons have twice the spin of the electrons. This is something which is impossible to reproduce if you say that these two entangled particles come out with some property P, and that property tells you whether Alice will see one polarization or the other, and Bob will see one polarization or the other. But these photons come all together in its spin total is S1 plus S2 is 0. Now if you look at all the books how this argument goes, the data is total spin 0, this is the prediction, and this prediction is impossible to reproduce such that a classical signal goes to this photon, classical signal goes to that photon, and the outcome of Alice and Bob's experiments only depends on the classical signal and the A Alice used here and the B Bob uses here. You cannot reproduce this answer. it is assumed, however, that both Bob and Alice have free will to choose their A and B. It's very important that this photon doesn't know what polarization Alice chooses, and this photon doesn't know what polarization Bob chooses, because Alice has not yet made up her mind, and Bob has not yet made up his mind. So while the photon moves to Alice, Alice makes up her mind, she chooses A, and the outcome of her experiment therefore can only depend on A and P. And P is some property that these photons have in common when they are emitted. And the same thing for Bob. Then you run into a straight, solid contradiction of this quantum result, and that's when people say there is no plastic signal going with this photon. Now, this is a very tough problem. And the first thing I've noticed is that, of course, Alice and Bob do not have free will. They cannot change their mind, because what they will do, whatever they'll do, is fixed by the laws of nature. And the laws of nature are deterministic. When they make a change, there must be a very big change in their past to make a small change in their setting. That is not enough. People, of course, realize that when they analyze the experiment and say, no, this is not the answer. Because if it were, then something very strange would be the case, because it would mean that somehow this decaying photon knows ahead of time what Alice is going to do. This photon knows ahead of time what Bob is going to do. How can that be? And if you phrase the problem this way, you indeed have a problem. I did a little calculation to see what is needed to get this thing back out of the mystery. What is needed is a correlation between the polarization of the photon here, these two entangled photons which have a joint polarization. They must have, otherwise it would be entangled. The A of choice of Alice and the B which is choice of Bob. And those three things are correlated. I should write it this way. There's a probability that there's a combination. I computed the minimal amount of correlation that you need between these things. And it turns out to be something like the absolute value of a sine of 4p minus 2a minus 2b. And that means there's a bit ability. If I plot say p against, well, 2a minus 2b, then I get a absolute sine function. Whereas the average would be somewhere here. And that means that yes, the decaying photon chooses a P which is correlated between Alice's choice A and B and Bob's choice B. And people now object, how can that possibly be? And well, my time is quite short, also I'll skip some of the stories which come on the internet. You know, how Alice makes a decision based on the signal of a distant quasar, and Bob makes a decision based on a mouse that he has in his cage, and so on. They're very silly stories. And how can it possibly these things be correlated? The answer is yes, they have to be correlated. And the reason is that in a deterministic theory, these are all variables. And the strange thing is indeed that Alice can rotate the polarizer, but this photon will know whether it goes through the polarizer. There never is a probabilistic distribution. It's always a variable. So whatever the outcome of the experiment is, it is a certain outcome. It's not a probability. The probability comes if you measure, if you're uncertain of things. If you're uncertain of the initial state, then there will be a probability here and a probability here. If you work as a variable, the outcome of the experiment is always unique and single. And so the answer I come in the very end is an ontological conservation law. And it says, that ontological conservation law says that if you start with a variable state, you will end up with a variable state. And whereas this experiment is formulated such that when this photon, this one half of the tandem particles, one is the particles reaches Alice, there's a probability that the photon will go through the filter or not. But then you haven't started with the Beagle state. Because the Beagle state, the photon knows whether it will go through the filter or not. And the same thing at both sides. So there you shouldn't work with probabilities at all. And in the very end, that means that things are not a little bit correlated, not even like science, they're completely correlated. You can also say the following thing. In the deterministic theory, I work with the state very, very close to the vacuum state. But the vacuum is not a Beagle. The vacuum is the lowest eigenvalue Hamiltonian, which is a superposition of all states. So right from the beginning, we assume that Bob and Alice live in something called the vacuum. But the vacuum is not what you might think it is. It's not a deterministic state. So from very beginning on, you work with templates and not with Beagles. Because you work with templates, you are getting into this concept. If you work with Beagles from the very beginning, you will never enter into such a conflict. The problem, and that remains an unanswered problem, is how to reframe all this in terms of fundamental Beagles at all levels. One thing is that we don't know the vacuum state anymore. The vacuum state is indistinguishable from states where the total energy is the Planck energy. So we have a big problem here in identifying what Alice and Bob would call the vacuum. Whereas it's very important if you do this experiment in an environment where you have temperature in the order of the Planck scale, Alice and Bob will not be there because that's a very, very violent environment. So the vacuum is a very special state. And so the answer to this apparent paradox should be found in that direction. But I do admit that I don't have an answer that completely satisfies myself, so let alone any of the audience. So there is still a problem to be addressed, but my proposal is to leave the problem whatever it is and try to solve this end of theory where I try to figure out what the Beagle underlying theory is of such a thing as a standard model. The hope is that we get new clues about the standard model. Also new clues about the vacuum state, and that's what this has in common with the conformal gravity which I had in the previous lectures, that also in conformal gravity we have a big problem as to understanding the vacuum state. The vacuum state is not what you think it is. Leaving behind the vacuum state, actually you would be in a conformal transformation of the vacuum state. And so there are difficulties in understanding the vacuum. So in the very end, maybe the problem is that you have to ask again. We are assuming within the vacuum state, and maybe that's part of the difficulty. That assumption gives us some pre-assigned knowledge about Alice and Bob behavior here. If we just assume some other states, you will never be able to predict what Alice and Bob will do. So this photograph will be able to predict it. Now it does. And but all this is still a mystery. I leave the mystery just as it is. I'm thinking models like a standard model, believing that there will be a natural answer along the lines that indicated. But I think these good things of theory are sufficient motivation to go on and think that this is the way you have to understand quantum mechanics. Now let's go to the Planck scale. Let's try to make models where some theory of Beagles reproduces quantum field theory. That will be priority number one. After we understand how quantum field theory works, we can try to make standard models, figure out which standard model is in agreement with that, and how do we understand Lorentz invariance and features like that, and conformal invariance. So all this we want to build in the good theory, and so we want to use all these clues given us by nature to theoretically construct something that looks like a standard model, and to find constraints on how to make a standard model. Having these completely